Hi and welcome to another video on meteorological instrumentation. In this one, we're going to talk about instrument design and selection, and we are going to focus our discussion on instrument standards. What exactly is a standard? Well, a standard is something that's agreed upon by everyone. It's something that's set up, established by an authority as a rule for measuring quantities and weights and extents so everybody can compare. And when we compare, we're not comparing apples and oranges, we're looking at the same thing. So we can all make estimates and value judgments. There are a number of different standards. There's calibration standards, performance standards, exposure, and also procedural standards. We're going to look at each one of these. Calibration standard, by definition, what is calibration? Calibration is where the magnitude of some output is related to the input. In the example that we have here, you're looking at a liquid and glass thermometer. And as the height of the mercury in the thermometer goes up, that's related to some temperature. So we can come up with some equation that says the change in height of 1 inch is equal to 20 degrees Fahrenheit. That would be a calibration standard. Calibration can be either static or dynamic. Static means that once again, the static means there's no time element. So the sensor input is held constant, whereas dynamic means the sensor input is changing. For example, you may be changing temperature over a period of time and seeing how the thermometer responds. Whereas static calibration would be just a particular temperature, you have a particular height in the liquid and glass thermometer. Change the temperature, you get a different height. Calibration standards are maintained by national laboratories. There are 2 national laboratories. Actually, there's 2 in the United States. They're both branches of NIST. NIST stands for the National Institute of Standards and Technology, and one is located in Boulder, Colorado. I'm not sure where the other one is. I forgot already. But the other local or other standard, other laboratory is the Bureau International des Poids et Mesures. I don't speak French. You could do that better than I can. But that's located in Paris, France, and that's where they have standards for measurements. What do we mean by standards for measurements or calibration standards? These are things that do not change and that everybody agrees that that is the value that we use. For example, the international kilogram, for the longest period of time, they had a cube of metal that was precisely 1 kilogram. And every device for weight was calibrated against that somehow, some way. Perhaps there were copies of that kilogram that were sent different locations, and then we developed scales based on those weights so that they measure precisely kilograms. And then those scales were calibrated or used to calibrate other scales, and so on and so forth. When you have this cascade from a national standard like that international kilogram down to your local bathroom scale, we call that traceability. In other words, you should be able to trace the calibration of your instrument back to the national standard, whether it be weight or seconds or whatever. So there should be some sort of traceability so that you can see that your instrument corresponds to a national standard at a laboratory. An example of this is peanut butter, believe it or not. There is a jar of peanut butter at the National Institutes of Standards and Technology that costs $800, $835. And this is NIST peanut butter. You've heard of Skippy, you've heard of Jif, but you probably never heard of NIST peanut butter. Why would a jar of peanut butter cost $800? Well, this is very special peanut butter. It's used in nutritional studies all across the United States. And in order to compare studies, you have to have peanut butter that is consistent. It has the same nutritional value. Now, everything is the same with this. It's a standard. So that's why there is peanut butter on a shelf at NIST that costs $800. And you know that choosy scientists choose NIST peanut butter. There are also performance standards. When we talk about performance standards, we're looking at terminology that describes the performance of instruments. And we already discussed some of this terminology. We talked about time constant. Everybody agrees that time constant is the time that it takes for an instrument to respond to 63.2% of a change of some input. Response time is the time that it takes for the instrument to respond to the complete change. So there are very well-defined terms that we use in describing performance, and those are our performance standards. There are also exposure standards, and these standards tell us where we can place our instruments to get a correct measurement. As you know, with wind speed, as you get closer to the surface of the Earth, the wind decreases because of friction. So there should be a particular height which everybody measures the wind. If you measure the wind in the US at 1 foot above the ground, and in Canada you measured it at 100 feet above the ground, then the wind speeds would not be very comparable. We want to have the same height so we can compare wind speeds. So that's why there's an international standard of 10 meters above the ground to measure wind speed. Also, there's a standard for where you should put your anemometer, how far downwind of obstacles, and that standard is 10 times the height of the tallest obstruction. So in other words, if you have an anemometer you want to set up in the parking lot of Clifford Hall, it should be about 10 times the height of Clifford Hall. Clifford Hall is about 90 feet, so your instrument should be, your anemometer should be about 900 feet downwind of Clifford Hall. There are other examples. You don't want to put thermometers in the sun because they'll be measuring only solar radiation and not air temperature. You don't want to put anemometers on the top of the building because, you know, as the wind blows over the building, it accelerates in wind speed. So there are all sorts of exposure standards. There are also procedural standards, and procedural standards are how we measure things. What is the procedure for measuring things? How often should you measure air temperature? How do you average the wind speed? Do you look at the last 10 minutes or do you average over the entire hour? Or is it just 2 minutes? So people have come up with agreements to how to measure these things. Some of these agreements are put in manuals. And here in the United States, we have a manual for making surface observations that report routine weather observations called METARs. Some of those standards include the time that we report these observations. Typically, these observations of the surface need to be made between 45 minutes after the hour to the top of the hour. In those 15 minutes, somebody needs to go out with an anemometer, a wind an anemometer or a thermometer or other instruments to measure weather properties to report those. Another example is measuring snow. How do you measure snow? If the snow is melted in some locations and it's a little bit thicker in the same field, do you measure the part that's thicker or do you measure the part that is bare? So there are actually rules for measuring snow, believe it or not. And then, of course, humans make measurements and machines make measurements. The problems with human measurements is sometimes they're subjective, but humans can measure things better than machines or instruments sometimes. For example, looking at the clouds, trying to make a measurement of clouds in a given location. Humans can look around and estimate how much cloud cover there is, whereas a machine really can't look around an airport and come up with an estimate of clouds. It can only look straight above the airport to see clouds. So sometimes humans are better at observing things, but also humans are rather subjective. If you take another person and have them look at the clouds, two people will come up with two estimates of cloud cover. So that's kind of not very standard. The nice thing about automated measurements is that they're rather cheap. It's much cheaper to have an ASOS machine or some sort of weather system than a human. Humans work 24 hours a day, 7 days a week, and they are not cheap. When you put a machine out there, it works for a long period of time before it has to be calibrated, so it's rather cost effective. Here's some numbers for an AWOS machine if you want to buy one. The North Dakota Aeronautics Commission gave me these numbers back in 2008. To purchase the ASOS, it costs 88 grand. It costs another 50 grand to install it, meaning to pour the concrete pad, to run electricity out to it, to run a data line out to it, and to calibrate it. And then have it report weather. Every month it costs $200 to have a network connection. So you can see it is pretty expensive up front, but in the long run, believe it or not, it's cheaper than a human. Also, you can put automated systems where nobody wants to make weather observations, where no human wants to make weather observations, like in Crookston or Thief River Falls. No human wants to be there. And of course, humans tend to get really bored making repetitive measurements. So as a result, they start to make errors. There are human errors as a result of repetition. And the nice thing about humans, though, is that they're intuitive. They can look at measurements that were made by instruments and then look at those and actually do quality assurance. Are those instruments making the correct measurement or not? So sometimes it's really helpful to have a human in the mix there, making quality assurance. So those are some things that we are concerned about when we're talking about instrument standards.